Okay, good morning, everybody. So this is going to be on the exam. Okay, if I can have everyone's attention. So this is the last thing we covered, is the reaction of more reactive carboxylic acid ester derivatives to form lesser reactive ones. And the last one we looked at was the formation of amides. We're going to see a couple of different ways to form amides today. Don't worry about them for the upcoming midterm. You are responsible for these methods of amide formation, and the mechanism is very similar to the mechanisms we've seen so far. Because we have a reactive acid chloride, in this case an acyl chloride, a reactive carboxylic acid derivative will react with an amine, which is a good nucleophile. We have a nitrogen with a lone pair of electrons that attack the carbonyl carbon, form our tetrahedral intermediate, and then we can kick off, in this case, chloride, and at the end we end up pulling off a proton. With the formation of amides, because we're using those amines as our nucleophile, they're also quite good bases, so we often have to use one equivalent extra of the amine, because we end up with our final product having a protonated amine as well, because we're forming an acid, a strong acid, HCl, in the course of this reaction. So that's something to remember. Similarly with, if we used an anhydride, a similar thing would happen. With an ester, we don't have to worry about it, because with an ester, the acid that we form is just an alcohol, and that's not a strong enough acid to protonate an amine. With carboxylic anhydrides, same thing, because we form, in the course of our reaction, one of the products is a carboxylic acid that will react with an amine to form the amine salt. And with esters, again, we don't have to worry about it, because the acid that we form is an alcohol, which is a very, very, very weak acid. We can also make amides by just reacting a carboxylic acid with ammonia. We end up getting the ammonia salt, and then we just heat this. We try to do this neat, and we heat it, and we end up getting this amide. We'll see a little bit later that we can hydrolyze amides, so we can do the reverse reaction as well. The one I want to talk about today now, this is used extensively, particularly for biochemistry. A way to make amides is through what we call DCC-promoted amide synthesis. DCC is simply dicyclohexylcarbodiimide, and I'll draw the whole structure up here. Yeah, simple, eh? So this is dicyclohexyl carbodiimide, and we usually just call it DCC. If you take a look at this, hopefully you may not see this, but this is isoelectronic with carbon dioxide. Okay. Now, why is this important? Well, we have nitrogen, which is somewhat electronegative. We can draw resonance structures, but we can see that this is an electrophilic carbon. So let's go through the mechanism for the DCC-promoted synthesis of an amide, and actually your textbook gets it a little bit wrong. So what we do is we have our acid, and I'm just going to use and we have our carbodiimide, and I'm going to do this because I don't want to draw that big cyclohexyl ring all the time. So I'll just put CY for cyclohexyl. The first thing that happens is actually simply a protonation. Now when we do that protonation, I'm going to draw it like this, and then we have our what we've done is we've activated our dicyclohexyl carbodiimide. We've activated because we've protonated it. We've made this even more electrophilic carbon. So the next step in the reaction, we simply, we don't need this anymore, protonate. Now we have this compound. So we've actually activated now. We haven't activated, but we have a very good leaving group. Okay, so you'll see here oops, I'm going the wrong way. Your textbook kind of complicates things a little by talking about, oops, why did I go so far? Oh no, sorry. A little bit by showing this. The first step is actually a protonation step. Although this mechanism will also lead you to the right place, it's not strictly, you won't see it very often. If you do an internet search, you'll see a mechanism more like what we're doing on the board. So now our amine is there as well, and now our amine, and I'm just going to use diethylamine, will simply react Actually, I'm going to do this, okay? I'm going to do the stick figures thing instead of drawing it all out because I'm lazy. We have to put a positive charge here. Now there's a few different ways we can do it, but one of the things we want to recognize is that protons jump on, protons jump off. Something puts a proton on, something pulls a proton off. Something's going to pull that proton off that nitrogen, and where do you think I want to put it? I want to move it. I don't want to move it to the oxygen up there. I want to leave that up there just for pushing arrow purposes. One of the things you want to remember, when you do an amide coupling reaction, you're forming water. It's a condensation reaction. When just a carboxylic acid plus an amine gives you an amide plus water. And what this cyclohexyl carbodiimide, dicyclohexyl carbodiimide, is actually doing is sopping up water. So we've already sopped up one proton in the first step. We're now going to move this proton over to the nitrogen. And so I'll put two arrows just so that we're aware that it may or may not be intramolecular. And when we do that, now we've set it up so we can just push all of our arrows and get to our final product. We're just going to reform this carbon-oxygen double bond, and our leaving group is now going to leave. And when it does so, we get the formation of our final products. Okay? We formed this thing, which is dicyclohexyl urea. Okay? Notice now, hydrogen, hydrogen. It's sopped up the elements of water, right? It's basically sopped up H2O. Now, why this is such a good coupling reagent? Number one, it does provide a mechanism for a carboxylic acid to add to something and form a nice leaving group. But the other nice part about it is it forms this thing. As it turns out, this dicyclohexyl urea is quite insoluble in a lot of solvents, and it just comes out of solution. Everything else stays in solution, and it provides a nice, easy means of purifying our amide product. And this is our product that we were hoping for, our amide product. Okay, so at first, do you have a question?
Yeah. I was just wondering, you do the double arrow thing a lot when you're drawing reaction mechanisms. If we were writing a midterm or an exam and it asked us to draw out the mechanism, like, are we supposed to draw 2 arrows, or are we expected to know the steps in between? Or?
You kind of are expected to know the steps in between, yes. If you drew the 2 arrows, you would actually be showing me that you know that the proton doesn't just hop from that nitrogen to that nitrogen. That's all it's indicating. I could go through and draw everything. Well, there's only one intermediate in there.
Okay.
And that is a base comes about and removes this proton, and then the base floats around and puts the proton in the other place.
So on a midterm or an exam, should we draw the intermediate step, or do we draw the 2 arrows?
Whichever you're comfortable with. I would mark this correct.
Okay.
I would mark this correct, and if you did the other, I would mark it correct.
Okay.
One of the things I've been trying to get across in this is that we draw these mechanisms. There isn't just one absolute right mechanism. There's different ways to do things, okay? Sometimes, if we take a look at that, that's moving from 1, 2, 3, 4. You could actually have a 5-membered transition state. You could envision drawing something where that would happen all in one step. Because, let me just draw the skeleton there. We have an NH2 bonded to a carbon, bonded to an oxygen, bonded to another carbon, and we now have a double bond to the N, okay? And that has cyclohexyl. The rest we don't care about. I just drew. Does everybody see what I just drew? I just drew this skeleton from here up to there, okay? So in fact, with that, let me get my charges right. This is positively charged because it also has that on it. We can actually draw our arrows like that and show an intramolecular. Now, a lot of times you're not going to have that. And all I'm saying is instead of bothering to look and see if you can do that intramolecularly, understand in some cases it can happen intramolecularly. In many cases it cannot. Just because it can happen intramolecularly doesn't mean it can't happen through a series of proton and acid-base reactions, okay? So really all this is indicating to me. Now if you happen to draw one arrow and said that you had a 1, 2, 3, 4, a 1,4 proton shift, that would be fine. That would also show me, that would actually, well, slightly impress me that you would recognize that you had a 5-membered transition state where a proton can move. And whenever you have 5- and 6-membered transition states, then that's a very facile reaction to happen intramolecularly. But, so we got a little sidetracked there. Don't want to confuse anybody, but good question. Okay, so the answer is do what's comfortable. I'm going to mark that right with the 2 arrows. Unless I specifically said something like show all proton transfer steps. Now, what I wouldn't want to see though is from here to here with 3 arrows. Okay, I want to see that. Okay, I suppose you could just go from the starting material with the correct number of arrows into the products. You could make a guess, but no, I want to see most steps. So the reason this is such a good coupling reagent is because the formation of this provides us an easy means to clean the reaction up. And that's why it's so popular in the lab. And here's just more of the mechanism the way your book shows it to you. So again, this mechanism isn't necessarily wrong. It could happen as well. So in other words, this step could happen. It's just much more likely that you're going to get a proton transfer in the first step of the reaction. This is a decent enough base, and it's not a strong base. So this equilibrium where we had this equilibrium would not be significantly to the product side. It's just once it gets there, the rest of it happens fairly rapidly. A little while ago, we saw where we heated up the carboxylate salts of a carboxylic acid and ammonia to form an amide. Well, we can hydrolyze amides under both acidic and basic conditions, but they're quite stable, and we have to add a lot of heat to them. And that's good for us because these amides are so important in terms of structures in our bodies that it's nice that they're not easily hydrolyzed. Mechanism is as you would expect. The mechanism is the same for the acid catalyzed hydrolysis of anything else. The first step is the activation of the carbonyl group by protonating the carbonyl oxygen. That activates the carbonyl carbon to attack by even mild nucleophiles such as water. Then once we get to here, we can do a series of proton transfers to get to here. Notice now, in this case, we'd have a 1, 2, 3, 4-membered transfer state. So you should actually have 2 arrows here. 2 sets of arrows the way I've been doing things. In other words, this isn't likely to happen intramolecularly. That's a very unlikely event because of the 4-membered transition state. But once we get that proton transfer, we can just knock off ammonia. The last step, the ammonia is going to react with our protonated acid to form the ammonium, which is missing here. The other side product of this reaction is NH4+, and the carboxylic acid. Under basic conditions, let's think about this reaction coordinate. So here we have it under basic conditions, and what we have is our amide gets attacked by hydroxide. And then this is our tetrahedral intermediate. The most likely thing that's going to happen is it's just going to go back and kick off hydroxide. When it kicks off this compound, that's not very energetically favored. Because this is amide. It's actually just amide. It's a very, very strong base. Hydroxide's a strong base, but amide is a much stronger base. So going this way is very unlikely. But once we get to this direction, the last reaction will drive this reaction. And the last reaction is simply an acid-base reaction. This drives the reaction. So now that we have that up there, let's think about the reaction coordinate for this reaction. We haven't looked at reaction coordinates yet this year. At least I don't remember it. But we have to be aware of the energetics of reactions. So over here we have some form of energy, probably some form of free energy, and this is just our reaction coordinate. So we started off with our amide and hydroxide, and we talk about the nucleophilic attack of the oxygen to form this compound. That's going to be higher in energy, a little bit higher in energy because we go from forming hydroxide to forming something like an alkoxide. It's not going to be a lot higher in energy, but a little bit higher in energy. The next reaction where we kick off ammonia, that is actually going to be significantly higher, okay? And then our final reaction is way down here. And if we think about what's happening energetically, there's going to be a bit of an activation energy here. There's actually going to be quite a high activation energy here. This last step, once it gets to here, it really only has one way out. And the activation energy to get from here to here is very small indeed, because we have a strong base reacting with a fairly good acid. It's a weak acid, but it's a pretty good acid. So that's actually what drives it, is this last step. So most of the time it's just going to go ping back and forth between these two, right? Every once in a while you have to heat it. Yeah, that's the reason you have to heat this reaction, is to get over this barrier. So once you get over that barrier and it kicks off the ammonium, the amide, that amide is a very strong base, and if it meets that acid, it really only has one choice, and that is to go down here and form the carboxylate and the ammonia. Okay, so that's our reaction profile. This represents the tetrahedral intermediate, and this represents okay, and that thing is not happy under these conditions. Okay, so as soon as that's formed and it sees a carboxylic acid, it says, hey, I can grab that proton, and boom, it gets down here to your products. This is kind of similar to the base-induced hydrolysis of an ester, kind of the same idea. With an ester, though, you don't have to add heat because you don't have this very strong barrier. You're not forming a really strong base. You're just forming a base that's a little bit stronger than hydroxide. We can dehydrate amides. One way of dehydration would be breaking it back into the carboxylic acid. I'm sorry, that would be a hydration. We can dehydrate an ester by removing 2 molecules of hydrogen and a molecule of oxygen and form a nitrile. We usually need pretty strong reagents to do this. We need things like P4O10, or acetic anhydride will do it as well. We have to add some heat to these reactions. We can also use thionyl chloride, and look what we get. We get our nitrile, and we get the formation of acid. Quite often we put things in to sop those acids up, but we don't have to. Let me see how much time we have. We'll take a look at the mechanism. Okay, so let's take a look at this mechanism with acetic anhydride. There's acetic anhydride, and I'm just going to push my arrows like this, and I get, I want to draw this in a certain way. Okay, so we get RCO. The only reason I'm moving it is because of this bar. We get RCO. What was the, yes. And I'm drawing this because I want to draw a cyclic transition state to just show you how easy this next step is, okay? So notice now I've just formed a bond between this oxygen and this carbon. That's this bond right here. Okay, and this is just our tetrahedral intermediate because we've added, this is, in this case, this is our nucleophile, and it's adding to acetic anhydride, which is very electrophilic. Okay, that's why this reaction will go, that first step will go. That's the new bond we formed. We broke the carbon-oxygen double bond, and we have a pair of electrons up there. And now, when we push our electrons back, we can reform our carbon-oxygen double bond, and we can, oops, sorry, forgot my positive charge there. Now we can form a bond between that oxygen and that hydrogen and kick off this bond. And we end up getting this thing. I'll put that in a box. That's our acetic acid. And we have, oops, sorry, didn't want to do that just yet. Sorry, didn't want to do that just yet. We now have this thing. This is a tautomer. Notice what this looks like. Did we get rid of? Yep, we're good. We're good. So now what we can do is we can imagine, we can draw this. Let's do it over here where we have room. I'm going to redraw that. Okay, so I've just redrawn that so that we can have 1, 2, 3, 4, 5, 6 member transition state. And now we can just begin pushing arrows. We can remove that proton, form a carbon-nitrogen triple bond, and we can reform that double bond, and we get this thing. We form our nitrile, and we form our acetic acid. Okay, so these are our products, 1, 2, and we formed another molecule of acetic acid over here. Okay, so we have two subsequent reactions in which we can achieve this 5-member transition state in this particular instance. When we use something else like thionyl chloride, we actually have to throw something in that's basic to sop up the elements of water. In the case of acetic anhydride, it works because we get these nice, easy transition states which allow this reaction to go to completion. But what we have done, in effect, is remove water and form a carbon-nitrogen triple bond to form the nitrile. Why might we use this? Well, it's easy to make a nitrile from an alkyl bromide when we have a primary alkyl bromide, because this reaction goes under SN2 types of conditions. It's more difficult when we have secondary and tertiary alkyl bromides, because they don't like to go via SN2 mechanisms, and it's difficult to get the conditions such that it favors an SN1 mechanism. What ends up happening is this thing actually ends up acting more like a base and favoring elimination reactions. So it's difficult to make tertiary nitriles through the substitution using sodium cyanide. So what we do instead is end up making the alkyl bromide, reacting with a CO2, working it up to getting the acid, making the acid chloride followed by ammonia to make our anhydride, and then reacting that with something like P4O10 or thionyl chloride or acetic anhydride, and we add some heat and we can end up making our nitrile that way. So synthetically, this is useful for those times when we can't make our nitrile through a simpler process. Hydrolysis of nitriles, they are a carboxylic acid derivative, so they can undergo hydrolysis as well. They're catalyzed by both acid and base. How much time do we have? And I want to talk a little bit about, oh, we're good. Okay, so acid or base and a bunch of heat will add water across that carbon-nitrogen triple bond, and we end up adding it a couple of times, and we get our carboxylic acid through hydrolysis. So we can use either acid or base. Both of them, though, we have to add a lot of heat. The mechanisms, it's not as hard as it looks here. So let's go through it on the board. That looks complicated. Let's make it step by step, make it a little simpler. So we have a nitrile. We have a lone pair of electrons, and although we have water, the first step in a reaction, we're going to do it under acid hydrolysis. Here's a hint, and it doesn't happen all the time, but for most reactions where you're using acid as a catalyst or there's acids around, almost always the first step will be a protonation reaction. Almost always. Okay? So that's what you want to think about. Where would this protonate? Well, it's going to protonate right there. And the first step in our reaction then and really what makes this harder is they're showing that a resonance structure for that. So what we've done is exactly what we do when we protonate a carbonyl group. We've activated the carbon of this C triple bond N functionality, because we can draw a resonance structure where we put the positive charge on that carbon. So now I'm just going to react that with water. and this is just going to lose a proton. This is another thing you can do. Those two arrows, perhaps what I could say is minus H plus H plus when you're getting protons moving about. But look at this thing now. Okay. Hopefully what you can see now is we've lost our H plus. Here it is. Now we can just okay, and now, well, does anybody recognize this thing? What is this? What if it's just a protonated amide, right? This thing is what we call a tautomer of an amide. This is an amide tautomer. How many people know what a tautomer is? You guys talked about tautomers. It's just an isomer. It's really an isomer of an amide. A tautomer of an amide is a particular thing. Everything's in the same position. The only thing that's different is the protons have moved. The skeleton remains the same, and this proton ends up over here, and we have a carbon-oxygen double bond in the amide. So now we just have to, this is just hydrolysis of an amide, which we've already been through. I'm actually not going to expect you guys to know the base catalyzed hydrolysis, and we'll go through it up here on the board, and I'll explain why I wouldn't expect you to know it. It's much the same. We get a nucleophile attacking the most electrophilic carbon to form this thing. This thing then reacts, and now again we kind of have tautomerization. What makes this reaction difficult, we end up attacking that carbon, getting this thing. At some point, look at this species. And this is why we really have to heat this reaction up. We have to pull off two protons, and we end up with this dianionic species, okay? One of the reasons for invoking that is it's hard to imagine it going by any other mechanism. One of the reasons I don't want to expect you guys, I think it forms bad habits to start forming these dianionic intermediates. This requires a lot of energy, okay? So this is, in most instances, you shouldn't be drawing things with two negative charges on oxygen. And that's one of the reasons why I don't expect you to memorize it. Just realize that it happens. We can have lactams just like we can have lactones. When you have cyclic carboxylic acid, when you have a carboxylic acid that has a nitrogen on the delta carbon, you can form a delta lactam. If it's on the beta carbon, you can form a beta lactam. Even though these things are hard, this is actually a very important functionality in medicinal chemistry. Anybody know why? Anybody know what that's found in? That's found in penicillin, okay? And it's actually quite reactive. This is penicillin works by a suicide mechanism. It actually attaches itself to its host and ends up making it so it can no longer undergo the molecular recognition events that make you sick. So beta lactams are important. They're difficult to form, and there was a lot of work done on how to make beta lactams. We're not going to undergo any of that. Oh, I meant to, this derivatives of carbonic acid, I do think I have the next hidden. Just take a look at it. You're not going to be responsible for this section. Decarboxylation of acids, you will be responsible for this. And this is one of the things I want you to remember. It is important. It's important synthetically. We use it a lot. we'll use it a lot in later sections. Making beta-keto acids. Beta-keto acids readily decarboxylate. And the reason they readily decarboxylate, it's kind of a theme of today. A beta-keto acid, I'm going to draw it slightly different. RCOCH2 O. Sorry. C. O. I'll get it. If we draw it slightly differently, all of a sudden we can see that nice six-membered structure that we're getting used to seeing now, and we can simply push our arrows where we So this thing is entropically driven. This reaction is entropically driven. The reason it goes is because we can form a nice six-membered transition state that allows all the bonding changes to occur without a conformation that can't be achieved. Once that reformation of the bonds occurs, the CO2 just migrates away and the reaction goes. This thing is just what we call an enol. And it is in equilibrium with the ketone. Okay, we're actually going to make use of these things a lot in chapters 18 and 19, these enols, okay? But it's an important thing to remember is that this decarboxylation of beta-keto acids occurs quite readily. Decarboxylation of carboxylic acids themselves is not really very favorable. It's difficult to make happen. There is a way to make it happen. You can make it happen, we'll see in just a second, through radical reactions. But here we see the beta-keto acid forms the enol. The anion also decarboxylates fairly readily, and one of the reasons is because this particular thing, which is called an enolate, happens to be much more stable than we might otherwise think, because we can draw a resonance structure to get the charge off of the carbon and onto the oxygen. So that thing is much more stable than we might otherwise think. We can also make these things happen for regular acids by turning them into radicals, usually through electrochemistry. We remove an electron from a carboxylate anion, and we get this carboxyl radical, and they readily decompose because carbon-centered radicals are slightly more stable than oxygen-centered radicals, and that's why that occurs. I'm going to skip that because we already did it, and we're done with chapter 13. So there's some things in chapter 17 you're not responsible for. They're hidden on the slides. And that's it. And we have 5 minutes, so any